The network layer of the internet has a specific job: the physical routing of data packets from one host computer to another. Modern end systems handle multiple network processes at once. A single server might simultaneously process email transfers, a live video stream, and database queries. The IP packet gets the data to the correct building, but it cannot determine which specific room needs the delivery. This diagram shows the architectural layers. The transport layer sits above the network layer, elevating physical routing to logical process-to-process communication. Routers use NSAPs, IP addresses, to locate the physical machine. The transport layer defines TSAPs, or ports, where applications listen for connections. Because this layer deals exclusively with application logic, transport protocols are implemented only in the end systems. The intermediate network routers process physical routing, completely blind to the transport layer data passing through. The transport layer decouples applications from the physical network topology, allowing software to communicate logically through dedicated ports. When engineers build applications at this layer, they face a strict architectural choice: prioritize raw throughput or guarantee absolute data integrity. If the application demands speed and can tolerate some packet loss, like live audio or video streaming, the ideal tool is the User Datagram Protocol, or UDP. This table outlines the minimal 8-byte UDP header. The top row handles multiplexing, with a 16-bit source and destination port, ensuring the datagram reaches the correct application. The bottom row contains message length and an optional checksum, UDP's only basic data integrity mechanism. To maintain its lightweight profile, UDP strips out almost everything else. There are no handshaking dialogues, no guarantees on packet order, and no protection against duplicates. UDP functions strictly as a best-effort delivery system. It trades reliability for speed, leaving the application layer responsible for managing any network unreliability. Best-effort delivery is useless when missing or scrambled data is catastrophic. You cannot download a software executable or receive a financial ledger if random segments of the file are dropped. For those applications, the internet relies on the Transmission Control Protocol, or TCP. TCP is a stateful, connection-oriented protocol engineered specifically to mask the inherent unreliability of the subnet. The core hazard of internet architecture is that packet lifetimes are bounded but highly unpredictable. Due to router congestion or bad topology, a packet can become trapped in a circular pathway, continuously looping while other traffic passes normally. This creates the delayed duplicate scenario. A connection request from an old, closed session might break free from a routing loop and randomly arrive at a server minutes or even hours later. If a server blindly accepts that delayed request, it will assume a client wants to communicate. The server will allocate memory and processing power to establish a ghost connection that no one actually requested. The engineering challenge is clear. Two disconnected computers must guarantee that a connection request is current and legitimate without possessing an omniscient view of the network's traffic. The explicit mathematical solution to the delayed duplicate problem is Tomlinson's three-way handshake. Look at this diagram detailing TCP connection establishment. It requires 3 steps to safely synchronize 2 hosts. Step 1. The initiator sends a SYN segment containing an initial sequence number, represented here as X. Step 2. The responder replies with a SYN ACK segment. It acknowledges the sequence by sending X plus 1 and proposes its own sequence number, Y. Step 3. The initiator acknowledges by returning Y plus 1, synchronizing both sides. This diagram shows what happens when we test that mechanism against a network failure. Here, the failure is triggered. Host 2 receives a delayed duplicate connection request from an old session without host 1's knowledge. Host 2 reacts by sending an ACK segment back, effectively asking host 1 to verify the connection. Host 1 checks its active state, realizes it wasn't establishing a connection, and issues a reject command. Host 2 abandons the ghost connection immediately. The three-way handshake functions as a rigorous synchronization of sequence numbers. This mechanism ensures that both hosts are current, rendering accidental connection establishment from old packets mathematically impossible. Once TCP successfully secures a connection, its job shifts to resource management. It constantly regulates the speed of data transfer to prevent a fast transmitter from overrunning a slow receiver. This requires buffering. The sender must hold all transfer protocol datagram units, the TPDUs, in local memory until the receiver explicitly acknowledges that they have arrived intact. The transport layer must also manage these active connections across limited physical router space. This illustrates upward multiplexing. Multiple transport layer connections are bundled together to share a single underlying network virtual circuit, maximizing cost-effectiveness for data heading to the same destination. Conversely, when a network has slow capacity, the protocol employs downward multiplexing. It splits a single transport connection across multiple network paths to artificially boost throughput. An active TCP connection is a dynamic entity, continuously adapting its buffer sizes and multiplexing routes based on live network feedback. The final critical phase of a TCP lifecycle is safely tearing down the state machine, ensuring the connection ends without accidentally severing data that is still in transit. In an asymmetric release, like hanging up a telephone, the connection is broken instantly for both parties the moment one side disconnects. TCP requires a safer approach. TCP utilizes a symmetric release protocol. It treats the virtual path as two separate unidirectional connections. Each direction must be released independently. Looking at panel A, we see the normal operation for a successful teardown sequence. Host 1 sends a disconnect request. Host 2 replies with its own disconnect request. Both sides follow up with acknowledgments, definitively releasing the connection in both directions. Panel D poses the ultimate failure scenario. What if the subnet swallows the final disconnect request? TCP has a built-in failsafe. After repeated failures, a timeout threshold is reached. The sender unilaterally releases the connection, preventing a permanent drain on system resources. Whether an application demands the stateless, raw speed of UDP or the rigorous, self-healing state machine of TCP, the transport layer provides the critical logical bridge that allows the modern internet to function.